My name is Toshihiko Sasaki, and I'm from Kanazawa University, Japan. I'd like to talk about the two-dimensional X-ray diffraction method and its application to RCF of rails. The sample of the rail used in this study has been used in service for a business line for about 7 years, and it has a 17 millimeter long crack. A list of authors is shown at the bottom. The first author is myself. The second author is Dr. Kayoko Yanagi. She contributed the X-ray measurement. And the third author is Dr. Shingo Mitsui. He contributed the hardware development of the X-ray equipment. And Dr. Ryutaro Nishimura contributed the software development. Okay. As you all know well, this slide shows the RTF process of rails. As shown here, in rails, plastic flow and white etching layer and cracks occur. Finally, fracture of rails occur, and derail accident has been occurred in the past. The countermeasure to this RCF at the present is ultrasonic testing for detecting cracks and the grinding of rails for removing damaged layer before crack initiation. In my talk, I'd like to show that a newly developed two-dimensional X-ray diffraction method is effective for monitoring the early stage of the RCF. Sorry. The X-ray optics and equipment used in this study was shown in this slide. First, we measure diffraction ring from the rail by using a two-dimensional X-ray detector, for which we used an image plate, IP. And next, we calculate the stress using strains obtained from the diffraction ring by using the so-called cosine alpha method. Details about the cosine alpha method will be explained later. The right picture shows the experimental setup used in this study. It consists of X-ray equipment and X-ray stage and a high voltage power supply and a computer. The X-ray equipment was hung from the XY stage to automatically conduct continuous measurement by X-rays. The X-ray measurement time for stress was about 2 minutes per point. This speed is almost 10 times faster than that of the conventional X-ray method. The sample rail used in this study is shown in this slide. It's classified as a Japan Industrial Standard JIS 60 kilogram rail. The length of the sample was 123 millimeter, and it had a 70 millimeter long crack, which was detected with the ultrasonic testing method. We can see crack branching on the surface of the rail. The picture at the bottom shows a cross-section of the rail, showing wear on both of the corners. This picture shows the sample surface of the rail head. The X-ray measurement was carried out on the rectangular area shown by the dotted red line in the picture. The longitudinal area of this area, the length of the area was 120 millimeter, and the transverse length was 40 millimeter. The X-ray measurement was conducted in this area with 2 millimeter interval. The total number of X-ray measurement points was 1,260. This slide shows 3 examples of the diffraction rings obtained from the layer. These were measured from the positions shown by the white arrows in the picture at the bottom. We can see the width of the second diffraction ring is thicker than those of the others. In the right top figure shows the profiles of the intensity of the diffracted X-rays in the radius direction from the center of the ray, center of the diffraction ring. It's shown that the width of the second ring is larger and the peak intensity is lower than those of the others. The cross-section of the position where the second diffraction ring was measured is shown at the bottom, showing that there is a white etching layer beneath the surface. It's known that the martensitic transformation occurs in the white etching layer, and the martensitic transformation layer makes the diffraction ring very thick and the diffracted X-ray profile much wider. In the next slide, we focus on the full width at half maximum, which is defined as the right figure of this slide. This slide shows the 2D mapping of the FWHM for width at half maximum obtained from the rail. The definition of the FWHM is shown here again. This plot consists of all data measured from 1,220 points. As a result, we can see that there are 2 sharp peaks on both sides of the graph. The place where the peaks were, where these peaks generated consists with the place where the white etching layer was generated. Second, we can see a shallow depression around the center of the graph. There was a crack here, so this depression was caused by the crack as well as by the repeated passage of trains after the initiation of crack. At the next step, we calculate the residual stress by strains obtained from the diffraction ring. This slide shows the process for determining strains and stress from the diffraction ring. The so-called modified cosine alpha method was used to stress determination in this study. When using this X-ray optics, we can obtain the 2 kinds of triaxial shearing stresses, tau xz and tau yz, where x is the axis parallel to the running direction of the train. The y-axis is the transverse direction of rail, and the z-axis is the depth direction. The other 4 triaxial stress components, such as sigma x, sigma y, sigma z, and tau xy, can be obtained by a similar manner using the other diffraction rings obtained from the different directions. Details shown in my paper. The result of the stress calculation is shown in the slide. Shearing stress tau xz is plotted here. Tau xz acts as shown in the upper right figure. We can see that there are 2 features in the mapping of tau xz. One is the relaxation of stress around the center of the rail. As a crack formed near the center, it's thought that the restraint in the surroundings of this area disappears due to crack initiation, which makes which made the stress relax. The second feature is the difference in the stress between the gauge corner side and the field corner side. The stresses on the field corner side from the center line of the rail show positive values, whereas on the field corner side, they show negative values. It's known that the plastic flow of the surface layer of the rail has opposite direction between the gauge corner and the field corner side. The behavior of the shearing stresses tau xz corresponds well to that of the plastic flow. In other words, we can detect the state of the plastic flow from the X-ray measurement. Line profiles of tau xz are shown in this slide. 4 lines were selected and compared. The first line and the fourth line cross over the white etching layer. The second line crosses over the crack. The third line crosses the area without white etching layer and crack. As a result, similar stress distributions are seen in the result except for in the second line. In the second line, it can be seen that the stress is relaxed or has negative values on the field corner side. This change is thought to be due to occurrence of the crack. Whereas it seems that the change is small at the gauge corner side. Finally, I'd like to summarize my talk. First is that 3-axial stress measurements were conducted by the two-dimensional X-ray diffraction method on a cracked rail that was used on a business line. 2 kinds of shearing stress, tau xz and tau yz, and fluids that have maximum FWHM were obtained simultaneously within 2 minutes by using the modified cosine alpha method. Second, it was found that stress tau xz relaxed at the position where the crack occurred and correspond well with the plastic flow generated in the surface layer of the rail. Third, FWHM is increased remarkably at the white etching layer. The fourth, the state of the cracks and the white etching layer and plastic flow in rails can be detected from the residual stress and or FWHM measured by X-ray. Thank you very much.